Sets of numbers. Our objective is to classify and order the real numbers. Why learn this? Sets can be used to organize the balls used during the billiard game 8-ball. We should probably look at some vocabulary first. A set is a collection of items called elements. A subset is a set whose elements all belong to another set. The empty set is a set containing no elements. It's empty. Roster notation is where the elements of a set are listed between braces. For example, in words, the set of billiard balls is numbered 1 through 15. In roster notation, 1, 2, 3, 4, all the way through 15. And you have braces to close it off. A finite set has a definite or finite number of elements. Similar to our billiard balls, it has a finite number. You don't have billiard ball number 1.37, nor do you have billiard ball number 18. It has a finite set of numbers. An infinite set has an unlimited or infinite number of elements. In interval notation, the symbols with brackets and are used to include an endpoint in an interval, and the symbols with those two parentheses are used to exclude an endpoint from an interval. For example, 3, 5, as an interval notation, is a set of real numbers between but not including 3 and 5. This chart might help. So we've all done graphing before, and we know that when you have numbers that are less than without an equal to, it's an open circle. The open circle is very similar to your parenthesis, whereas the closed circle is similar to your brace. You use them interchangeably. Just depends on which style of notation they're asking for. So for numbers less than 3, it doesn't stop. It keeps going all the way to infinity. Well, in the negative direction. So negative infinity is to your left, and 3 is to your right, and both have basically an open notation. So a parenthesis on each side. Open circle, parenthesis. And because you have an infinite, you can't have a singular number for infinite, so you can't include the value of infinite. Doesn't make sense. So you always make sure that it's a parenthesis when you're dealing with infinite. Numbers greater than or equal to negative 2. So greater than or equal to negative 2. So because you're including the value of negative 2, you use the brace, and then it's going off into positive infinity. And when you've got infinity, you have a parenthesis instead of a brace. But can you do more than one number? Well, yeah. Numbers between 2 and 4. So between 2 and 4. This was very similar to the vocabulary word that we were looking at. So you're not including the values of 2 and 4, just everything between them. So you're going to have a parenthesis on either side, or both sides, of the 2 and the 4 to show that you're not filling it in and that value is not included. But everything between them is. As an inequality, this should look pretty familiar. Well, if you're filling in the circle or you're including the value of 1 and 3, you're going to use that brace. Hopefully this chart helps make a little more sense of the vocabulary word. And then we have set builder notation. It uses the properties of the elements in the set to define the set. This is kind of like having it have a rule. We'll look at that momentarily. Let's start by ordering and classifying real numbers. So consider the numbers 0.6 repeating, the square root of 2, 0, negative 5 divided by 2, and 0.5129. We're going to order the numbers from least to greatest. So to help, why don't you write each number as a decimal to make it easier to compare them. Now that you've had a moment to write these as decimals, let's see what we had. So the square root of 2 is about 1.414, and negative 5 divided by 2 is negative 2.5. So let's order the decimals. Our smallest decimal is going to be our negative, so negative 2.5. Then we have 0, and then we start into our positives. So we have 0.5129, 0.6, and then we're into 1.414. Your answer, however, should not be in the decimal form that you made it into. You should put it back into its original form. So negative 5 divided by 2, 0, 0.5129, 0.6 repeating, and the square root of 2. You've all seen these before. Natural numbers, whole numbers, integers, rational numbers, irrational numbers, and they're all a member of the real numbers. So, in the past, you didn't have a nice little symbol to slim things down. No, the symbols are for the sets of numbers. So, the set of natural numbers, which is 1, 2, 3, through your counting numbers, you would use an N, and there's a little double line in there to indicate that you're not just using the letter N randomly, it's talking about the set of numbers. So, symbols are important. Well, a whole number, you basically have all your natural numbers, but you also get to include a 0. An integer includes the 0, the 1, 2, 3, 4, 5, all the way up, as well as the negatives, so your negative whole numbers. Think of it as a Venn diagram. So everything in this circle is also a part of the whole numbers, but not every whole number is a natural number. Your rational numbers are anything that you can make as a fraction. You can make 2 a fraction, 2 over 1. You can make negative 5 a fraction, negative 5 over 1. You can make 2 and 7/9 a fraction. You can't really make pi, e, the square root of 2, and then fractions that are completely accurate. So they're irrational. They're irrational numbers. Take a moment and try to fill out this chart. When you return to the video, the answer will be revealed. So where the check marks are what they are. So for example, negative 5/2 is a real number and a rational number. It's not an integer. Just because it has a negative sign doesn't mean it's an integer. An integer is all your natural numbers, your whole numbers, and then your negative whole number values. Okay, and let's look at some more examples. Alright, so we want to use interval notation to represent each set of numbers. So when you look at this inequality, you notice how you have a less than or equal to and a less than. So the symbol that goes around the 4 is going to be a brace, whereas the symbol that goes around the 6 is going to be a parenthesis. Because you're including the value of 4, but not including the value of 6, just going all the way up to 6. This one gets a little trickier. My suggestion is to do each piece separately and then write them together in the end. So let's look at the piece on the left. Both values are included, as well as everything between them. So for interval notation, we're going to have a brace around both of them. And now let's look at the other piece. You have an open circle at 3, and then it goes off into infinity. So you're going to have a parenthesis at 3 because you're not including it. And then because it's going off into infinity, you always put a parenthesis around infinity. And now let's put it together. So it's either going to be this value, or it's going to be 3 through infinity. And that's interval notation. So why don't we take a look at the set of striped billiard ball numbers, or, in case you're wondering, those would be the numbers 9, 10, 11, 12, 13, 14, and 15. So we briefly mentioned when we were doing the vocabulary that set builder notation is like talking about a rule. Well, a rule in math is just a formula. So when you're doing set builder notation, it's a set, so you've got your braces here, and the set of all numbers x. What this is saying is that, hey, we're dealing with this number x. And this little line here, meaning such that, kind of says, okay, this is the variable. Now I have my rule to the right of this line. It's like it separates it. But you need it in there because you don't want to think of it as x times 8 randomly. So that little line your such that line, will separate the variables you're talking about with the rule. Now the billiard balls are the numbers 9 through 15. It doesn't include the value of 8. So therefore, it's a less or greater than, so 8 is less than, so a less than sign, and then you have a less than or equal to sign for 15, because you're including the value of 15. 15 is one of the balls. Now, you have to be very careful, because you don't have any billiard balls labeled 9.7. They're very clearly labeled with whole, or natural numbers rather. So your natural numbers, your x, is going to be the element of all the natural numbers. So let's try this out. The set of all numbers x such that x has these given properties. 8 is less than x, is less than or equal to 15. So we know it's got to be between 9 and 15. And x has to be a natural number. So it has to be like a 9, a 10, 11, a 12. And that is set builder notation. This chart might help. The methods of set notation. We've talked about roster notation and interval notation, and we just finished talking about set builder notation. So let's look at here. We have the words, all real numbers except 1. You can't write it in roster notation because you can't write it similar to something like this. However, you can put it in interval notation. So it's all real numbers except for 1. So if you were to say all real numbers, that would just be infinity. Negative infinity to positive infinity. But since we're trying to cap it off and get rid of this 1, you're going to cap each end off at 1 because we're going to exclude that value. It's not a brace, so we're not including the value of 1 here. And in set builder notation, we're talking about the variable x, and there's its rule. If you're talking about positive odd numbers, 1, 3, 5, 7, they keep going. That's why you can't necessarily use it in interval notation, because you're not talking about all the values in between. But in set builder notation, you can limit it to only be talking about the natural numbers. Let's try a set of examples. Rewrite each set in the indicated notation. Pause the video and try them, and the answer will be revealed when you come back. And there are your answers. So for A, you had just the positive even numbers. For B, you had 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then your 2 asterisks here. And then for C, you had x such that negative 3 is less than x, which is less than or equal to 5. And that ends our lesson on sets of numbers. If you have any questions, please ask your teacher.